Our fourth lab is the single train and compound spur gears. In this lab, we're going to do performance analysis of three different types: single train gear arrangement and one compound spur gears. The learning objective is that we'll learn what is single and compound gear trains, why they are different and how they're different, and then we'll learn to assemble four different gear train systems, and for all those four train systems we will determine the velocity ratio, mechanical advantage, and efficiency for each gear train, and we'll conclude with the comparison of those, what is the advantage and disadvantage of each other's arrangement compared to each other. So what is a gear train? It is a series of mating gears. If you see on the image on the left and the right, you see there is gear on shafts and they are meeting with each other. So together they are forming a gear train. It is used in almost all machines for large velocity change in limited space. If you see the gear train on the left, the green, blue, and red, they have different size and also they have different teeth, and that's how they have different rotational speed compared to each other, and that's how we change the velocity from one shaft to another. Our focus for this lab is on simple gear train and compound gear train. So how they are different. So on the simple gear train, one basic difference from the compound is that there will be only one gear in one shaft. On the other hand, for a compound gear train, on the right image you see the green is connected with yellow, and then the blue gear is connected with the red, and then the middle shaft has two gears, blue and yellow, in one shaft. So if there is multiple gears in one shaft, that is a compound gear, and if it's in a series, then we can call it compound gear train. A second difference is in the way it transfers the power. For a simple gear train, power transfers through meshing gears. If you see on the left image, if you assume that the green one is the driver and the red one is the follower and the blue is the idler gear, then the power transferring from the green to the red. Now see, the power from the driver is transferred to the blue and then to the red only through the meshing gears. On the other hand, if you look at the compound gear train, the power is transferred through meshing gears and the shaft. How? Again, if you assume the green is the driver gear and yellow is the follower, and for the next round the blue is the driver gear and the red is the follower, then the power is transferred from the green to yellow, and then from yellow to the blue it is transferred through the same shaft, and then from blue to the red it is transferred from the meshing teeth. So that's why for compound gear, power transfer is completed through meshing gears and shaft. Another difference from simple to compound is that for simple gear train, the size of the teeth has to be the same because they are mating with each other, and there is only one gear per one shaft. On the other hand, for the compound gear train, since one shaft has multiple gears, those multiple gears in one shaft can have different teeth size. So for the green to yellow, you can have different size teeth, and from blue to red, you can see here you can have different size teeth. Since blue and yellow, they are not mating each other, they are just on the same shaft, and that facilitates that you can have different size teeth on a compound gear, but for simple gear, all the teeth has to be same size. So we have reviewed what is single gear train and compound gear train. So now, just to assess yourself, look at the gear arrangement in the picture and comment whether you think it is a single gear train or a compound gear train. Now we're going to talk about the direction of the power transfer. If you see the both gear arrangement, they are just mirror opposite to each other. Now the direction of power depends on the driver and follower gears. If my green is the driver and my load is attached on the red one, so that will be the follower, then my power transfer will be from green to blue, blue to red gear. And the same gears, if I put the red as a driver and put my load on the follower, then the power transfer direction completely changes. So now the power transfer direction would be from the red to blue and blue to green. So the power transfer direction depends which one is the driver, which one is the follower, and it follows from driver to follower. Now we will learn how to determine the teeth or diameter ratio. The teeth ratio is the ratio of the teeth on the driver over teeth on the follower. It is also the same if you take the ratio of the diameter of the driver over the diameter of the follower, because the number of teeth on a gear depends on the number of the diameter. And since between a melting gear the teeth size are same, so the ratio will be the same. Now to calculate the teeth ratio, we have to remember that we have to first find the power transfer direction to determine the teeth ratio. Because if you know the driver and follower, then you can find the teeth ratio. Let's give a name of our green, blue, and red gear like A, B, and C. Assuming A is the driver and red is the follower, then the power is transferring from left to the right, from green to blue, blue to red. If we count the teeth of each gear, assume that on the green gear you have 42 teeth, and on the blue one you have 28 teeth, and gear C has 14 teeth. So the teeth ratio from A to C would be the multiplication of A to B and B to C. So from A to B, the teeth on A, the driver, is 42, and the teeth on B is 28. Again, teeth on B would be again 28, and teeth on C will be 14. So teeth on B and teeth on B will cancel out. So the final ratio would be on teeth on A and C. So 42 over 14, just 3. So the teeth ratio for this simple gear train arrangement is 3. Did you notice that the middle or the idle gear, blue one, has no effect on the overall ratio? For example, if we didn't consider this multiplication, if we just take the first one and the last one take the ratio, we would have get the same result, 3. This is only valid for simple gear train where the middle gears are idle gears, and the idler gears have no effect on the overall teeth ratio. Now we're going to learn about the gear ratio, or we can also call it velocity ratio. One word we'll call it velocity ratio. So the velocity is inversely proportional to the number of gear teeth and the diameter. So the more teeth you have, or the bigger the diameter of the gear, the less is the velocity. So the red one is moving faster compared to the green one, because the green one has more diameter. So for this simple gear train, the velocity ratio is the velocity of the driver over velocity of the follower. Since it's inverse to the number of teeth, it is equal to teeth on the follower over teeth on driver. So let's find the overall velocity ratio for this simple gear train arrangement. For the velocity ratio from A to B is the teeth on the follower and teeth on the driver. So the follower has 28 teeth and the driver has 42 teeth. The ratio is 0.67. Now for this next stage, blue to red, velocity ratio from B to C, or blue to red, is the teeth on the follower, which is 14, and teeth on the driver, which is 28, and it is 0.5. So the overall velocity ratio from A to C would be multiplication of this 0.67 to 0.5, which gives you 0.335, which is exactly inverse of 1 over 3. Remember on the previous slide, we found the teeth ratio of 3. Now the velocity ratio is 1 over 3. So that is inversely proportional to the teeth ratio. Notice if your velocity is greater than 1, it's a reduction gear. If its a velocity ratio is less than 1, it's a multiplier gear. So what it means is that on this arrangement, power is being transferred from green to red gear. Since my velocity ratio is 1 over 3, my speed or velocity is being multiplied, or it is more than the driver. And it is likely because you have bigger gear, green, then smaller, red. So since you are reducing the diameter of the gear, the speed will be increasing. So that's why the velocity ratio is less than 1. If our power transfer direction is being reversed, then you'll see the ratio will be opposite. So now let's see how to find velocity ratio of compound gear train. So far on the previous two slides, we have learned how to find velocity ratio for simple gear train. Now we're going to learn it for compound gear train. The formula remains the same. Only difference is that for simple gear train, we saw there is no effect on the idler gear, but for compound gear train, all the gears will have effect. So the definition remains the same. For example, from A to B, the velocity ratio will be velocity of A over B, or the teeth on B, follower over driver. Same for velocity ratio C to D, will be the ratio of teeth on D, driver, and teeth on follower over teeth on the driver. In this case, it will be teeth on C, not A. So the overall velocity ratio will be the velocity ratio from A to B multiplied velocity ratio from C to D, same formula. If you put those, and you'll see the arrangement is such that the overall velocity ratio will be the product of teeth on the follower gears over the product of the teeth on the driver gears. So if we plug the values, the product of teeth on the follower gear, so in this case, first yellow is the follower of the green and the red is the follower. So for yellow has 14 and the red one has 14 teeth, so 14, 14. And the product of the driver gears, so green and blue are the driver, A or C is the driver, so you have 28 and 42 teeth. So the velocity ratio again becomes 0.167. So the velocity ratio is less than 1. That means it's a multiplier gear. The speed from the driver to the follower will increase, and you can see that the red one is a small gear, so the velocity will be higher, and that's why it's a multiplier gear. One thing just to note that the gear B and C, though they have different teeth, the yellow and the blue, they are on the same shaft, and that's why they will have the same velocity. For the different shaft will different velocity, but for all the gears on the same shaft will have same velocity. Once we have our velocity ratio, we can find mechanical advantage of a gear system and efficiency. The mechanical advantage is the ratio of load over effort. So how much load you're applying on the driver gear to how much load you are pulling from the follower gear, and how much load your effort you are applying on the driver gear, and the ratio will give you mechanical advantage. So if you plot load over effort, and the slope will be your mechanical advantage. If your mechanical advantage is less than 1, then the slope line will be load versus effort line will be like this one. If it's 1, it will be exactly going through this center middle of the plot. And if your mechanical advantage is greater than 1, then it will be above the mechanical advantage of 1 line. Now the efficiency is the ratio of the mechanical advantage over velocity ratio. And you see the efficiency, normally it will be 100, but in real life you'll see the efficiency changes. It starts from a little lower, then it goes a little higher, then it becomes plateau. The reason of this change, because when you're applying less or small load, the friction between gears plays a big role, and the efficiency, the losses is more, the efficiency is less. When you have more and higher load, then the loss on the friction of the meshing gear and other parts is comparatively less, and then the efficiency increase a little bit, and then afterwards it just plateaus itself. So for this lab, we're going to use the gear train kit for ES13 from Tech Equipment. On this gear set, you will have the board, and you will have different size gears and weights and weight hangers, so that you can arrange 4 different arrangements. So we will have 4 parts of this experiment. The first part is the part A, where we're going to attach a small gear, 2 small same size gear. What you have to do, you have to count the number of teeth on the both small size gear, find the velocity ratio, and you have to also find what is the rotational direction for gear A and gear B, both small gears. Is it clockwise or counterclockwise? Then you have to apply load on a driver and see how much effort you have to apply the load on the follower, and you have to see how much effort it takes to pull that load. So the load will be on the follower, and the effort you will apply, slowly increase the weight so that you know what is the exact effort to raise the load of 50. So we'll increase the load from, it's in gram, so 50 gram, 100 gram up to 400 gram we have to do, and for each of those we have to find mechanical advantage and efficiency. So this is the arrangement you'll do on the board, same size, small gear arrangement. The gear are meshing here at the bottom, and so this this is D is driver and F is the follower. So you will have a given load, for example 50 Newton, and you will keep adding load on the driver to see how much it takes to pull that 50 Newton, 50 gram on the follower gear. There is supplemental video link on this test available, given on the comment section. So for part B, now the gear size will change. We'll do different size gear. One will be smaller, one will be a little bit bigger than that, medium size. But the data collections are the same: teeth, rotational direction, and how much effort it will require for a given number of load, and you have to calculate the mechanical advantage and efficiency. So here you can see the different size, small, medium gear arrangement. This is the small gear, and then there's a medium sized bigger gear. And on the right image you see how they're not connected. So there is another gear size in the middle, so this big gear will be matching with the small gear here, and this is the front view. So how to do test with this medium small gear arrangement, the supplemental video for that is also given on the comment of this video. So for part C of this experiment, we're going to do a little bit different. We'll have an idler gear between two small gears. So the first part A will be there in the same arrangement, but between those two small gear there will be an idler, and the data collection remains the same. So this is the arrangement for a small idler, a small gear arrangement. So you see on the image we have a small gear on the left, and then this is the idler gear, and this is the small gear again. So they are attached, mating with each other, so they have the same teeth size. And supplemental video for this arrangement is also given on the comment. So for our last and final setup, part D, where so far we have used simple gear train. Part D will be compound gear train. The data collection are same as the previous one. Additional thing is that we're gonna count the velocity turns. So how much turn will have the driver gear, will have the follower gear B and C if you turn the driver gear A. So if your driver gear A rotates one rotation, how much it will rotate gear B and C, and from that you can find the actual overall velocity ratio, and we'll also have to find the overall ratio from counting the number of teeth, and we'll have to do the test for 50 to 400 as well. So this is the gear arrangement for the compound gear. You have there's double gear on the middle shaft, and there's one gear on each shaft. So the first one, if you see the right image, the first gear has one gear in one shaft. The middle gear you see here, it has two gear in one shaft. So this gear is mating with this gear, but this shaft gear is mating with another gear on the same shaft. So this shaft has two gears, this one and this one, in action, and that's why it becomes a compound gear. The supplemental video for this arrangement is also given on the link. So for our result, we have to calculate the mechanical advantages, overall velocity ratio, actual velocity ratio for the compound gear only, and the efficiency for all four arrangement. So for all four parts arrangement from A to D, for all four experiment, we have to plot load versus effort to see the slope will give you the mechanical advantage, and we'll also have to plot efficiency versus load. So together we'll have total 8 plots for 4 tests. So on the discussion section, you have to compare the advantages and disadvantages of the 4-gear arrangement based on your experiment. You'll have the mechanical advantage slope curve, so you will be able to compare for each arrangement the mechanical advantages, how they're smaller, bigger compared to each other, what is the advantages of having those. Then we have to compare the mechanical advantage, as I'm saying, for the 4-gear, and we have to comment on the advantages and disadvantages of each gear set, and then also the idler gear. So for final part, the part D, only for this compound gear, you have to compare the overall and actual velocity ratio by turning the gears. So you have to count how much the other gears rotate. If you turn one rotation of the driver gear, how much the other gears are turning. and from there you can find the actual velocity ratio. And finally, you have to list 5 real-life application of Spur gears. So in conclusion, as usual, you have to write a paragraph briefly summarizing the experiment, the main result, and any inference that you drawn from the experiments. These are the references, the textbook, and the Tech Equipment ES13 kit manual. So that was all for this lab. Our next lab is the displacement profile for various cams. Till then, take care. Thank you.